Just let me check if the sound is all right. Hello? Hello? Just let me check if the sound is all right. I see. Okay, so the sound is okay. Awesome. All right, so let's get started. So the idea of today's session is to give an introduction to the proof method called induction. We've seen induction a few times in our, most recently in our complex variable theory. In which we also encounter a little bit of a controversy actually. So today we're going to take a look at the foundations. What's the theoretical foundation for the proof of induction, and we'll do some examples. And we wish to cover both regular induction as well as strong induction. Both are very powerful techniques. Okay, so there's that. Today we're not going to say prove any sort of crazy result. Okay, we're just going to focus on the technique itself. Perhaps we will do one example, or perhaps we'll do a proof on the fundamental theorem of arithmetic, integer factorization. So yeah, we'll see how that's done. Okay, so this is a very powerful technique and it's very basic. But if you're new to proof, this can take some time to get used to, but hopefully it shouldn't be too unintuitive. Okay, so the induction proof are all about statement of this form. So statement of this form for all n in the set of natural numbers. Okay, I said for the set of natural numbers, but really it is about the subset of integers of this form. So this n, let's just put it n here, okay? And we can slightly change this set n to be something else. Okay, so for the moment, we'll just assume that the goal we wish to reach has this form. For every n in the set of big N, that's the set of natural numbers. By the way, in our convention, big N start from 1. I know there's endless debate on whether big N should start from 0 or 1. I start from 1 because I follow the analyst tradition. Okay. If you came from an algebra background or logic, you're perhaps more used to starting from 0. Hopefully we can agree to disagree. Okay. So N is the most common scenario. Big N is the most common scenario, or big N can be replaced by another set of this form. By a subset of the integers where a subset of integers big Z, okay, big Z, where the integers n is greater or equal to n naught for some n naught in Z. Okay, which means it includes n naught plus 1, and n naught plus 2, and so on, for where n naught is a number, is a whole number, is an integer. Okay, so for example, it might start from 2. That will be 2, 3, 4, and so on. It doesn't have to start from 1. Okay, but what matters is it starts from some integer, and then every integer afterwards is included. So you cannot skip things. So this is what induction is about. It's for proving statement of this form. And just review a bit about the statement Pn. So Pn is a statement about n. For example, n plus 1 greater than 3. That's a statement about n. Okay, and we'll see more of that later. It can get quite complicated. Okay, so how do we prove such statement? A classic way to introduce the idea of induction is the falling dominoes metaphor. So you got a bunch of metaphors, okay, which are labeled as P of 1 P of 2, P of 3, and so on. And actually, guys, this is going to be a long session, but if you want a more condensed version on Intro to Induction, please check out a video done by JC Practice Math. I'm just going to give the link right now. So yeah, I'll show you guys the playlist and the link. His channel is called Math Can Be a Hobby. Yeah, so this is his flagship series, Intro to Pure Math. Or actually, right now it's called Math Can Be a Hobby. It used to be called Intro to Pure Math. But yeah, so this is the series. And it's much more concise than these long forum live streams. So for example, you can check out he also did logic. Right? We did logic earlier, but this series is much more, shall we say, even-handed. Like my objective is to help people to get into rigorous analysis as soon as possible. So this has to do with my strategy for positioning the channel. Actually, my target audience is a general STEM audience who aren't necessarily math majors. Okay, they might have taken advanced math such as calculation-based calculus, but hadn't seen much rigorous proof by modern standard. Right. So, but for advanced subjects like, for example, machine learning and PDEs, stochastics process, proof writing is a must. Okay, so there's this gap. That's why we are making this bridge course. But JC's approach is much more even-handed. So he does not assume any background. Okay, not even say calculus or even pre-calculus, so to say. It really starts from the beginning. For example, you can see addition, multiplication, logic interlude. There's some overlap with what we're doing here, but he is taking a much more balanced approach. Okay, he doesn't just want to prepare you for analysis or any particular subject matter for that matter. Okay, so that's the induction. Where's the induction? My goodness, I've been talking about this here. Yeah, it is right. This right here. And prove by induction. So I'll put the link here. Yeah, that's this video. Okay, so for example, we have exercises on proving summation formula, which we will see today as well. And here, this is the link. I'll put it in chat and I'll put it in the stream description as well. Okay, and so go ahead and check out his stuff and his series. Fellow math creator. All right. Seems like my internet kind of sucked. Can we play it? Yeah, it's still loading for some reason. Okay. So yeah, that's Math Can Be a Hobby / JC Practice of Math, and we'll continue with our exposition. So basically, the metaphor is the dominoes for induction. This is a metaphor. Okay. So imagine you have P1, P2, P3 as dominoes, falling dominoes. So how can you argue that all of those dominoes are fallible, can be knocked over? Falling dominoes. That's the classic analogy. Well, think about how those crazy, what's that? The viral videos of knocking over dominoes. You show that you can knock over the first one, and then it triggers a chain reaction. Right? The first one knocks over the second one knocks over the third one, and so on. And then everything gets knocked over. So we're kind of doing the same thing for proving this statement. For all n in the set of natural numbers, P of n is true. So you prove P of 1. That's called a base case. And then you want to show for every n P of n implies P of n plus 1. And after that, you're done. Okay? And after that, you have guaranteed that for every n, P of n is true. So it's quite intuitive. But let's just give the formal statement, because we will be quoting this statement a lot when we do induction. Every time you write an induction proof, the last sentence should always be by the principle of mathematical induction. So we're going to state the principle of mathematical induction. That's a theorem. Okay, so let's see how that is stated. So theorem. This is actually quite a complicated theorem. If you're new to proof, this is perhaps a complicated theorem, and we will write the theorem in the form of hypothesis and conclusion, because that's always the structure of a theorem. You have certain hypothesis and a conclusion follows. So this theorem is called 3.1.1. Actually, we're following a book by Tamara Lakins. Tools of mathematical reasoning. Mathematical reasoning. In my opinion, this is the perfect bridge course proof textbook. Okay, it's not too worldly. A lot of the introduction to proof books, like I won't name any, but they feel to me to be too wordy. This one is concise, at the same time is also very approachable, and I like that. Lots of exercises and covers a wide range of topics. So in my opinion, this is a perfect textbook for a bridge course. Tools of mathematical reasoning. Okay, so go check it out. Okay, so the theorem says, the theorem is called the principle of mathematical reasoning. Oh, sorry, the principle of mathematical induction. The principle. Can't spell. Principle of mathematical induction. I'm getting better with my new mouse, but than yesterday, but still I need a lot of practice. The principle of mathematical induction, and it says the following: let P of n be a statement about positive integer n. I apologize if the writing is a little bit clunky, as I'm still trying to develop muscle memory for this particular mouse. So that n is a free variable, right? This is something that we discussed in our logic session. So on its own, P of n is not a proposition, because things like n plus 1 greater than 3 cannot have a truth value on its own. Its truth value depends on the value of n. So n is so-called a free variable. Okay, so here n is also a free variable. So that n is a free variable. That is to say, for a generic n, P of n does not have a truth value. Right? But if you fix n, then you can decide whether P of n is true or false. Okay, suppose the following, or let's write hypothesis. So there are two hypotheses. Hello, and welcome to the stream. So first you have the hypothesis, which we call PMI1. Okay, PMI1. PMI1 says the statement P of 1 is true. Okay. And then you have PMI2. So PMI2 says the following. It says for all positive integers n, That's the knock-on effect, okay? Um, but I thought you used Qualcomm. No, this is just a mouse. I don't have a pad or any tablets. This is just a mouse with Microsoft OneNote for all positive integer n, all positive integers m. Actually, let's write it this way. If p of m is true, you might actually hear the mouse clicking noise. Then p of m plus 1 is also true. So that's actually the most difficult part to verify. So here, p of 1 is you can think of it as the initiator. And PMI2, that's the knock-on effect. Okay, and that's a hypothesis. And then we can reach the conclusion as follows. The conclusion then says, for all positive integers n, p of n is true. So that's the formal statement for this falling domino metaphor. And every time we do an induction proof, we always say, by the principle of mathematical induction, blah, blah, blah. That's always the concluding sentence for writing induction proof. Okay, so induction proof has a very predictable structure, even though the specific technique used in a particular proof can take some ingenuity. But overall, that's the structure. And let's write the statement in symbolic format. So in symbolic format, that's the end of the theorem. Okay, so let's put a remark. In symbolic format, symbolic. Is induction is heavily used in Bayesian? No, no, no. This is a particular technique, and despite the name of induction, but this is really just a historical term. Okay, this is really a deductive method. This is a deductive method. The name induction, I think, is historical. Okay, it's like we're going from induction, generally speaking, it's like inference or something like that. I'm not a logician, okay? So don't quote me on that. It really is a deductive method. Okay, you check the hypothesis and you reach a conclusion. It has nothing to do with inference. Like Bayesian thinking is a statistical inference method. It has to do with updating your belief, updating the belief. Without experimentation, the belief is modeled as something called a prior distribution, without any data, without any experiment. And then when then data came in, okay, you make some measurement, and the belief, aka the prior distribution, gets replaced by the posterior distribution, and the update can continue, can be performed ad infinitum. That's the fundamental principle of Bayesian thinking. And as Bayesian thinking will be covered in the mathematical statistics part of the content. Okay, so this is really a deductive statement. There's nothing probabilistic, nothing uncertain about this. So yeah, let me first finish up the symbolic form, and I'll do the questions. I'll answer the question in chat. So in symbolic form, what does it say? It says you have P of 1, right? So that's the base case, what we call the base case, and initiator, this really should be called the base case. That's a technical term, and the PMI2 corresponds to what we call the inductive step. Okay, so this is the inductive step. So the base case and inductive step, actually, you usually emphasize which is the base case, which is the inductive step, clearly in the proof. Okay, so the inductive step says the following, right? So PMI1, and the inductive step says for all n, for all m, okay, for all m in big N, P of m implies P of m plus 1. Okay, so if both are true, so P of 1 and, let's use the and symbol, we've seen that in the first session on proof writing, intro to proof. This is a logical connective, it means and, okay? So, yeah, so if these two hold simultaneously, then we can say for all n, P of n. For all n, P of n. That's the symbolic form. Or you can write it this way in a slightly informal way, which says P of 1 and so basically the idea is this can be unpacked. For all m in big N, P of 1 implies P of m plus 1 can be unpacked to this form. So P of 1 implies P of 2, put a bracket here, and P of 2 implies P of 3. Okay, and then the pattern continues and so on, and it never ends. This will imply for all n, for all n, P of n. So that's the logical form. Okay, so but usually you work with this form because you cannot physically check P of 1 implies P of 2, P of 3 implies P of 2 implies P of 3, and everything after, right? So instead you do a quantify statement. You prove a quantify statement, okay? And here in the statement for the PMI, this is called PMI, okay? PMI, principle of mathematical induction. So if P of m is true, then P of m plus 1 is true. So when we write the induction proof, when we assume P of m is true, that's called an induction hypothesis. IH, okay. IH, okay. So this is induction hypothesis. And when we do the inductive step, you should always check whether the induction hypothesis is used. If the induction hypothesis is unused, that means definitively that you don't have a proof. Okay, so in the induction hypothesis is critical. We must use induction hypothesis to deduce P of m plus 1. Okay, anyway, so let me go read chat here. No worries. Thank you, Vizzy, for requesting it, actually. So how does this differ from proving P of n holds for an arbitrary n like epsilon proof in analysis? No, I don't think there's any difference. I don't think there's any difference. So for epsilon proof in analysis, actually, you mean the standard epsilon delta proofs in analysis? I don't think they're actually, it has something to do with induction. I'm not saying induction never shows up in analysis, no, but the usual epsilon delta proofs in analysis aren't a statement about integers. Okay, they simply aren't statement about integers, so induction doesn't work there. Okay, so I mean, for example, we did actually a proof in analysis in our first session. here, for example. There's multiple examples in our past lives. Okay, so here, if you see, where is that? I think it's we did that sometime in last month, probably. Yeah, intro to proofs, right here. Here, I gave the example last time as an introduction to analysis proof. Here, all you need in induction, all you need in, for example, proving the limit of a function is something, is this. It does not require any reference to integers. Or I guess, okay, so perhaps you're talking about the limit of a sequence. Perhaps you're talking about the limit of a sequence because sequence, say, is for sequence, okay? For a sequence, then the statement would involve integers. Actually, you know what? Let's go to, for example, our session on Zorich 1, where we discuss the definition of a limit, actually. Which day is that? Which day? Hang on, let me just find it. Okay, so yeah, this one right here. Somehow I didn't put a name, but this one is where we introduce a definition of limit of a sequence. So the definition of limit says the following. Here, yeah, this is the definition. The limit of xn, the sequence xn, is a if for every epsilon greater than 0 there exists a big N such that for all n greater than big N, x of n minus a less than epsilon. So for this part of the proof, so usually this is how it works in proving the limit statement. You let epsilon greater than 0. You try to find big N on scratch work, and in the formal proof, you just pick that specific big N or show why such big N exists, okay? And then try to verify the following, verify the box part. So in theory, this can be done using the induction proof structure we said earlier. Okay, so now you can imagine the base case would be big N plus 1. That's the, if you can verify, that's the base case. And then you say, okay, for every integer greater than big N, if the inequality, if this inequality is true, then it automatically implies the same inequality is true for xn plus 1. That will be an induction proof, although we rarely see that. Okay, theoretically, you can do so, but I cannot rule out such possibilities because, as we shall see, induction is useful for proving inequalities. Okay, sometimes induction can be helpful for proving this part of the limit statement. Okay, so how about that? Okay, I think that answers that question. So let me come back and let's just see more questions. Here, this question. Where is that? Okay. Currently just started using Zorich 1 and Shilov, yeah, for self-study. They are excellent books. Zorich looks a bit intimidating but interesting. I just completed a proof writing book, however. Okay, yeah, it's supposed to be. It's supposed to be Zorich. It's supposed to be like a, it's kind of like the baptism through fire experience in Russian institutions. So this Zorich is typically the book that Russian students decide whether math is for them. Okay, so it's supposed to be kind of a weed out experience. Although that sounds a little bit conspiratorial, I do believe with a good teacher, books like Zorich and Rudin are absolutely amazing. They will make you fall in love with math. But for self-study, unless you already have some proof writing experience under your belt, using them as a self-study source can be a little bit tough. Okay, but you can learn a lot. Seriously, you can learn a lot. Zorich, in my opinion, perfectly blends the applied side of calculus and the rigorous analysis all in one. So it's a perfect package, because that's the tradition in Russian style mathematics. They refuse to separate so-called pure versus applied mathematics at the introductory level. Okay, I'm not saying like every Russian mathematician is an encyclopedia. They do specialize because of, well, the finitude of human life. Right. So at research level, specialization do happen, but for example, in introductory calculus and analysis, the classic Soviet tradition is to emphasize the interconnectedness between various branches of mathematics, and it really inspires you to take a deeper understanding. So that's why Zorich is amazing. It looks a little bit intimidating for sure, especially volume 2. Especially volume 2. Zorich has 2 volumes, volume 1 and volume 2. Volume 2 is even more so, the multivariable stuff, but you can learn so much. Yeah, the use of the word induction has nothing to do with the philosophical induction, deduction terms from epistemology. Yeah, Christian, you nailed it. This is a historical term. It's kind of like, the annoying term called imaginary number. Even to this day, because of the term, some people still think the imaginary number or complex numbers are somehow fake. Okay, they're mathematical fiction that are convenient, but no, they're just as real as the real numbers. Okay, if you accept the real numbers, then you accept the complex numbers. That's it. Okay, there's nothing unreal about that. It's just a historical baggage. Once again, the proof by induction is a deductive method. You check the hypothesis and you reach a conclusion. Typically, induction, from a philosophical standpoint, is that you single out specific cases and then you make a generalized statement, right? But that's inference. That always carries uncertainty, right? It's like you see a bunch of swans that are white, and then you make the generalized statement and say, "Oh, all swans are white." That's an induction, right? It's not a mathematical induction because it involves uncertainty. There could be black swans, right? So there's that. Which book is being followed at the stream? Yeah, this one right here. Actually, you know what? I'll show you the cover as well. Here, that's the book, The Tools of Mathematical Reasoning, or the Z Tools, Z Tools of Mathematical Reasoning. I missed the article. The Tools of Mathematical Reasoning by Tamara Latkins. This one right here. It's not a very thick book, which I like a lot. This is meant to be, okay? This video series is meant to be, video and live stream series is about a bridge course towards rigorous analysis. Okay, a lot of the proof books, and this might be a little bit controversial, but I think a lot of the intro to proof book, there's too much hand holding. The pace is too slow, because my audience is already, my target audience, and I think an actual audience, are advanced undergraduate / graduate students from various STEM fields. I don't think they have the luxury of sit down through a first year style proof course for math majors. They just simply don't have the time. They wish to get into advanced research level stuff as quickly as possible to bridge that gap. So this is the book I'm following, okay? And this is not super long, and it covers a wide range of material. Language, logic, techniques of proof, induction, sets, functions, introduction to number theory, equivalence relation and partitions, finite and infinite sets, about cardinality, foundations of analysis. Okay, so these are this is the list of content, and on writing mathematics. Okay, so that's the book. Okay, actually this series is not going to be following one particular book. If you go to our series on introduction to proof and analysis, we actually kind of alternate between this one and quote unquote the advanced stuff periodically. So you learn something basic and then you can immediately apply it to more challenging material. Okay, so we did the quantifier, like logic quantifier, those stuff, okay, truth table, those stuff, and then we immediately dive into the definition of limit, continuity, Cauchy sequence, that kind of thing. Okay, so it's not like you have to go through every single section of it to do rigorous proofs. Okay. Anyway, so that's my guiding philosophy. The best way to learn a material is to apply it. I mean, not in the sense of applied mathematics, like real-world application, in the sense of using it. Okay, using it for both theoretical and practical purpose. Both are fine, but to master a skill, the best way is to use it. All right, so that's about it. Have more chat. I mean, induction involves assuming the hypothesis hold and that the result for the next integer follows. Yes. Why not directly prove P of n directly without induction stuff? Good question. Sometimes induction argument is easier, and sometimes induction argument, sometimes induction argument is easier because proving something is true directly for all n is difficult. For example, the famous example is the fundamental theorem of arithmetic. It says for every positive integer greater than 1, it has a prime factorization. How do you prove that directly, though? It's not easy, right? So induction sometimes feels like cheating because it has streamlined the proof for the statement for every n, P of n is true. And Christian answered that question. If you can prove P of n directly, that's equally good, exactly. Induction is just one more tool to add to your toolbox. That's very true. There are in fact black swans, right? So anyway, I think we're all on the same page now. Okay, so this is the fundamental principle that underlies the principle of induction. And actually, if you really want to get to the bottom of the foundation of proof by induction, it has to do with the definition of integers. It has to do with the definition of positive integers. So this is something called the Peano axioms. That's actually why I put the portrait of Peano, Italian mathematician, on the thumbnail. So Peano axioms are the fundamental assumptions, so to say, fundamental rules for the natural numbers. Okay, so the Peano axiom goes like this. Hang on. Where's the Peano axioms? Oh, actually, Peano axioms start from 0. Anyway, it doesn't matter. You can choose any base case. Hang on. What's going on? This is a historical second-order formulation. What we want, the modern version. Is that theoretic models? Perhaps. No, this is a model. I don't want the model. I just want the axioms. Where's the axiom? These are arithmetic operations. Hang on. Where do can we get a nice, concise description of the Peano axiom? Yeah, here. It's all based on just two things. You have a base case and a successor. If A is a number, then the successor of A is a number. Indeed, this is what kindergarten mathematics is about. Learning how to count. Counting, what is counting? Learning to count consists of the one task only, basically. What is the next number? That is kindergarten mathematics in a nutshell. What is the next number? Right? when a teacher in kindergarten asks children to count from 1 to 100, 1 is the base case, and children are supposed to know what is the successor of the previous number. So you have a successor, right? So 0 is a number, and 0 is not the successor of a number. So this is square 1. 0 is a square 1, and all the other numbers, all the other elements, okay, in the set of natural numbers are successor of some number. Okay, so this has to do, the foundation of induction has to do with how integers, how positive integer is defined. That's the theoretical foundation. Okay, so right now we're not going to spend an awful lot of time on the foundation, because this is mostly a bridge course, as I said, for applied scientists. Induction is a loophole. You kind of feel that way. It kind of feel like cheating, right? Because it streamlined the proof for all n, p of n is true, especially when it comes to proving summation formula. And speaking of which, let's do one. Okay, so here's the classic proof, example 1, proving the summation formula. Right, that's the sum of arithmetic progression, allegedly due to Gauss, but I'm pretty sure people before him know this formula. It's just that he discovered it himself at a very young age. I believe when he was helping his father to do some accounting stuff. So yeah, this is the summation formula, the sum of k, where k ranges from 1 to n, which is the same. Okay, it's just different notation, of 1 plus 2 plus all the way to n equals n times n plus 1 over 2. So that's example 1. Okay, so let's use induction to prove this. Okay, so first of all, this is, even though it is not explicitly stated as such, but we're assuming that n goes from 1, 2, 3, and so on. The base case is 1. Okay, the base case is 1. So here we have the base case. You have the P of PMI. Let's do the proof. Okay, so we start usually with this sentence. We prove the equation or the formula or the inequality depending on the statement. Okay, we prove the result, okay, by an induction of n. So we declare our strategy up front. It's a good practice. We prove the equation by an induction on n. Because sometimes there might be multiple free variables in a statement. Induction on n tells reader exactly what the structure of the proof is like. Okay, induction on n, which means you have a base case for n, and then you will show p of n implies p of n plus 1. Okay, and then we start by declaring this is a base case. So the base case is a statement when n equals 1. That's right, base case n equals 1. You can do an underline like this. So the left-hand side is the sum of k, and k ranges from 1 to 1, so which is just exactly one term. Okay, so that's the left-hand side, and the right-hand side, hi Tep, thanks for joining the stream. So the right-hand side is 1 times 1 plus 1 over 2, which is 1, and hence the left-hand side equals the right-hand side, i.e. the equation holds for n equals 1. There you go. So that's the base case done. Usually proving the base case is rather easy, but that still, it depends. Right? It depends. We'll see it in our second example why this might not be always easy. So that's the base case, and the inductive case is as follows. So the inductive case start by assuming the induction hypothesis as we stated in our commentary on the theorem. So it starts by assuming the induction hypothesis, and we say this: assume the equation hold when, or so we say if n equals m for some m, in the set of natural numbers. And we're going to say this is our induction hypothesis. And you can make it more explicit, and what we're assuming is such. So the sum of k ranges from 1 to m, is m times m plus 1 over 2. Okay, so for a beginner, a confusion might arise. Okay, this looks like exactly the thing that you want to prove. Why are you assuming it? Aren't you assuming the conclusion? No, of course we aren't. And here's the distinction, because the original statement isn't just this equation. It is a quantified statement. The original statement says for every n equals 1, 2, 3, and so on, the equation holds true. What we're assuming is for some m, this is true. So they aren't the same thing, even though the equation, of course, are the same. Okay, so that's another way to appreciate the importance of quantifiers. We're assuming, okay, one of the dominoes, okay, in somewhere, a domino somewhere in this setup is knocked over. We want to show that this automatically implies the next one is knocked over. Okay, so and a good way to remind ourselves what is our objective is as follows. We can write need to show, and this is a totally legit proof writing statement and strategy. You lay out what is needed, okay, without writing need to show. The reader might get confused. Okay, so this is the assumption, and if we change m to m plus 1, are we assuming that too, or is this something that you wish to show? Be very clear about that. You need to show the statement is true for, right, the equation holds for m, let's write equation hold, not let's say if, for 4. That flows better. The equation holds for m plus 1, so that's our goal here. For m plus 1, i.e. the new summation formula, the sum of k ranges from 1 to m plus 1, and this is equal to m plus 1 times m plus 2, okay, over 2. So our goal here revolves entirely around reaching this goal. Okay, so let's do so. This is the inductive, sorry, not base case, but base case, not inductive case, but rather inductive step. Okay, inductive step, my bad. Did I write that? Inductive step, yeah, inductive step, not inductive case, inductive step, proper terminology. Okay, so what do we do? Of course, this sort of proof for summation formula is extremely streamlined. The standard strategy is to group the first m term, use the induction hypothesis, and then add the final term, simplify. That's the strategy. The sum over, okay, over sum over k, sum of k from 1 to m plus 1, of course, is the sum of k goes from 1 to m, and plus the final term, which is m plus 1. Okay, and here you can use the induction hypothesis. So the first summation of m numbers, happy Tuesday. So that's a m plus 1 times m plus 2 over 2. Okay, well, that's wrong. What am I doing? What am I doing here? The formula is here, m plus 1 over 2 plus m plus 1. And write by the induction hypothesis. It's a good practice to always indicate in the inductive step exactly where the induction hypothesis is used. Okay. So sometimes when you're in a hurry, you can simply put an IH on top of the equality where the induction hypothesis is used. That's also okay. When you take notes and whatever, just want to give a quick indicator of where the induction hypothesis is used, this is a nice way to do so. And now it's just a matter to simplify this expression. So let's do the simplification. To simplify, we get m times m plus 1 over 2 plus m plus 1. Notice that m plus 1 is a common factor. So we can factor it and write m plus 1 times half m plus 1. But of course, this is exactly m plus 1 times m plus 2 quantity over 2. And that's exactly what we needed. Right? So this is also a nice way to, in our proof, a nice practice in proof writing. Whenever we write need to show, okay, we conclude with, we finish that, okay, like with a as needed. It's almost like writing a left bracket and you complete that with a right bracket. Need to show, blah, blah, blah. And when that's done, say as needed. And also, it's very common to say claim something, claim blah, blah, blah. And then you prove the claim. When the claim is proved, you write as claimed. Okay. It's just a good way to organize the proof and make it more readable. Okay, so now the inductive step is done. And now it's time for the concluding sentence. Therefore, we write, therefore, by PMI, what we want, the statement that we want is true. The sum of k ranges from 1 all the way to n, is n times m plus 1 over 2 for all n in the set of natural numbers, and that's the end of the proof. Okay, so that's it. Okay, so induction proof usually works very well for summation formulas. Let's say you have you want to prove another summation formula like the sum for the geometric progression. You can also use induction argument, right? Somebody said earlier in chat, are we doing any structural induction today? No, this is very basic stuff. This is meant to give a first introduction to induction. We're not doing any sort of mathematical logic here, okay? This is very much a lesson in elementary algebra, in elementary in the Russian system in particular. I think in Russian universities, in high school, they teach induction proof, right? But not so much here in most Western countries. Okay, so but really, yeah. So this is the a first example of induction proof. What we learn from this is not just the specific technique, which aren't many, but rather the key phrases, the key structure that helps to keep the proof organized, and at the same time strictly follows the hypothesis and conclusion of PMI. So this is like standard sentences that should be included in any proof of induction. We prove blah 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 by induction on n. Base case. Here, the base case is n equals 1. Sometimes the base case requires a little bit of a thought. Now, which one should really be the base case? And then the inductive step. The inductive step begin with assuming the induction hypothesis. Okay. Do not skip any of these words. Do not skip for some m in big N. Otherwise, there's risk of confusion. Is m a free variable? Right. It's like does m is an arbitrary integer? If m is considered as an arbitrary integer, arbitrary positive integer, then we have a problem because you're assuming the conclusion, something I just clarified. Okay. Induction hypothesis, and you want to put forth your goal. Right. Assuming the equation holds for n equals n plus 1, and clearly identify exactly where we use induction hypothesis, and finally by PMI, blah blah blah. So these are all mandatory statements, mandatory words, phrases in induction proof. So induction proof is usually highly structured. You can actually lay out most of this stuff without actually knowing what you're doing, which can be a good thing. It helps us to make baby steps towards reaching the final proof. Okay, so obviously this one is very straightforward. Okay, and sometimes, especially when it comes to proving inequalities, you might want to do some scratch work. For example, in the inductive step. All right, let's see an example. Another example of saying proving the induction, you prove by induction. Okay, so I'm actually going to modify the PMI a little bit. You can, here, this is PMI. You can modify PMI of 1 to say P of n naught is true. P of n naught is true, not necessarily 1. You can start with arbitrary base case. And then the second part will be for all integers n greater or equal to n naught. Then P of m implies P of n plus 1. Okay, and the final conclusion would be for all positive integers n such that P of n, so for all integers n greater than n naught. Okay, so it's just a shift of the base case. Okay, so let me just copy this and do some slight modification. Modified PMI. Okay, and we will use the modified version to prove an inequality. Okay, so the base case doesn't have to be 1. And sometimes actually you need to think a little bit to say, for example, in the induction, in analysis proof, right? In analysis proof, usually you need to show there exists a big N, right? It basically says for big N sufficiently large, then for every little n greater than big N, some inequality hold. But to get to that big N requires a little bit of exploration and what we call it the scratch work, right? So PMI modified. So sometimes the base case isn't already given. Okay, we'll do so shortly after we modify the statement. So here, the statement says P of n naught is true for some n naught in the set of integers, for some n naught in big Z. Okay, so that's the base case. And then PMI2 is now changed to for integers m greater or equal to n naught, the knock-on effect is true. So that's what we want. Usually this is the hardest part, usually, but not always. Okay, and the conclusion would be for all integers n greater or equal to n naught, P of n is true. So that's the modified PMI. Question, do we have to assume m is an integer different from the base case? No, it doesn't have to. Here, just like here, you see, for some m in big N, which big N includes 1. Actually, you know what? It has to include the base case. It must include, if it doesn't include the base case, the metaphor breaks, right? So the base case, say, is P of 1. In the inductive step, it must include P of 1 implies P of 2, and P of 2 implies P of 3. If you don't have, say, in here, so in the base, in PMI2, if your M does not include 1, that means we don't know whether the first domino can knock over the second domino. So the chain reaction might fail at the first step, and the whole argument collapses. There's actually an example for that to happen, which we'll show later. So it's a fake induction proof that shows, quote unquote, allegedly, okay, shows that all the horses have the same color. You can fake induction proof from it, and we'll see exactly where that fails. Okay, so to answer the question, we need the m equals 1. And here, you see, in the base case, we have P of n naught, and in the inductive step, we must have m greater or equal to m naught. This must be true for m equals n naught as well, not just strict inequality. Strict inequality is not sufficient. Okay, so that's the modified statement of PMI. And let's see an example. Okay, so let's see. This is an interesting example because it actually takes us a little bit of a scratch work to figure out what is n naught. Okay, so here we will. This is a very intuitive statement. Example 2. Example 2 says the following. It says, for sufficiently large integers n, we have n cubed less than or equal to 2 to the n. You know, computer scientists love this. Right? Polynomial, n cubed is a polynomial, right? Polynomial always gets beaten by exponential. This might be some sort of algorithmic complexity. Usually the computer scientists write big O notation for example, O of n squared, O of n times log n. Right? So these are orders of magnitude for complexity of an algorithm. So usually polynomial complexity is preferred because in the long run, okay, for large n, is always more efficient than exponential order algorithm with exponential order complexity. That's what I mean. But this can happen. The idea is this happens eventually, right? For small n, this might not be true. For example, when n equals 2, on the left-hand side is 8. On the right-hand side is 4, so that is actually not true. So for n equals 2 is false. The point is, this is true eventually. It's kind of like the definition of a limit of a sequence, right? There exists a big N such that whenever little n is greater than big N, an inequality holds forever. Right, so here, we wish to prove n cubed less than or equal to 2 to the n for some let's say for n sufficiently large, for sufficiently large n. Okay, and when we write a statement like this, for sufficiently large, for sufficiently small, this is super common in analysis. What this means is, namely, i.e., there exists a big N in the set of sufficiently large. I need to emphasize it's the integer, or sufficiently large N in the set of natural numbers. Okay, I'm saying is there exists a big N in the set of natural numbers such that for every little n greater or equal to big N, the inequality holds. Little n cubed is no greater than 2 to the n. Eventually, the exponential always wins. So this is a statement. So this is a statement. I'll come back to, yeah, so this is a statement. I'll answer the question right now. Good books for probability problem solving and math problem solving in general. Well, math problem solving in general, I'm not quite sure, like, because that's too broad, right? But for probability, it really depends on your level. But if you want to look for a challenge, you can go check out a classic problem set on probability. Is a problems in probability by Shiryaev. Shiryaev probability problem. There's actually a lot of problem books I would like to recommend. So the first one, we'll actually maybe do something about this, a video or live on Shiryaev probability problem. Problem in probability. So this is a classic. Do we have a cover page? Yeah, problems in probability. Because this covers both undergraduate and graduate stuff, so don't get, say, discouraged if you find yourself unable to solve these problems, because it's meant to be like, it's a book that is not meant to pat yourself in the back. Okay, this is something that Russians don't do. They make you really learn stuff. So this book is a classic, and let's say if you're preparing for some quant interview, this is a must-have. And what else? What else do we have here? Paul Helmus, Linear Algebra problem book. Helmus. This is a classic on like mostly proof-based linear algebra book. Okay, but let's say if you want something that is more approachable, you can check out Paul Helmus's linear algebra book. Okay, the actual textbook he wrote. It's called Finite Dimensional Vector Space. Finite dimensional vector space. Actually, you know what? The Google prompt gave me an interesting book title called Finite Dimensional Linear System. What's that supposed to be? Okay, and it's actually this cover, this dark green cover is usually a classic in applied math. I'll have to check it out later. So it's about solid foundation of learning a dynamical systems, linear differential equation. Oh, I have to check this one out. This is awesome. Okay. Okay, anyway, but I'm talking about the textbook by Helmus. And this is the perfect companion for that one. It's called Linear Algebra Problem Book. Okay, and for calculus, go check out Demidovich. Problems in Mathematical Analysis. It's a Soviet classic, over 3,000 problems. Limits and continuity, derivatives, differentials, indefinite, definite integral, series, functional zero variables. So this spans over the entire calculus series. And most of the questions are quote-unquote computational, but there's a nice progression of difficulties, as well as differential equation. So this is a great resource, available for free. So it contains the Russian style problem books usually start with some examples, and then followed by a lot of problems, of course, and sometimes may or may not include solutions. But usually, typically, they always have answers, like a number or a final formula. Okay, so these are the 3 books which I strongly recommend. Demidovich for calculus, Paul Holmes for linear algebra, and pair that with the finite dimensional vector space. This also has exercises which goes along with the main text. Sometimes Holmes would ask you to check a specific detail in the main text as exercise, and of course the probability text, probability problem set by Shiraev. Shiraev also have, as you can see, accompanying textbooks. What they ask in quant interviews mainly: math, programming, and finance, usually. Okay, yeah, math, programming, and finance. Now, there's actually a book on quant interview prepping. I'm not a quant, okay, so if you want like quant specific information, I believe there's a guy on YouTube called Dimitri. I forgot his last name. Dimitri. Quant. YouTube. Yeah. This guy, right? Yeah, this guy. Yeah, he does dedicated quant stuff. And I believe he has some math too. Does he still do math? It's mostly just news and stuff. I don't know. I believe he used to have actual math courses. Yeah, Python for quants, good stuff. Time series. Go check out his work. Okay. But overall, on this channel, we try to just focus on not the news, okay? We're trying to focus on the more evergreen style stuff, like just mostly actual math. That's what I prefer doing. Okay. Anyway, so that's a nice break. Now let's come back to So now let's come back to this example. So of course, you need to do the scratch work. Like we need to know what kind of n we're looking for, right? So exploration. Why don't we do a table? Okay, so this is n, and this is n cubed. This is n to 2 to the n. No worries, no worries. Thanks for dropping by. N equals 1. You have 1 and 2. Oh, actually, let's put another row. Is the statement true or false, right? N cubed less than or equal to 2 to the n. Is this true? Well, this is true. This is true for n equals 1. What about n equals 2 then? That's an 8, that's a 4. So that's not true. Okay, so big N equals 1 doesn't work, because big N need to satisfy, it's a threshold, right? So everything after big N, the inequality is true. So little n equals 1, or so we say, big N equals 1 doesn't work. This is not sufficiently large n. Where am I from? I originally from China, but right now I live in Canada. So n equals 1, 2, 3. What about 3? Well, this is 27. So this 8 is also not true. And then 4. What's 4 cubed? That's 16 times 4, right? 16 times 4, that's 64. Okay, 2 to the 4, that's a 16, so this is also not true. Wow. 5, what about 5? 5 is 125. 2 to the n, that's 32, still not true. Keep going, 6. So 6 cubed is what? 16 times 6, that's 96. 96, and 2 to the 6 is 64. That's also not true. Keep going, 7. Then 7 to the third is 49 times 7. Okay, let's just put it this way. Okay, 49 times 7. Okay, 49 times 7, actually. Let me write it, get the final result. Okay, 49 times 7, this is 3 times 6 get carried over, so that's 28 plus 6, 34. Yeah, 3, 4, 3. What's 2 to the 7? Well, 2 to the 7 is 128. That's not true. And 8, what about 8? 8 cubed is 64 times 8. So that's a 2. Put 3 up here, and this is, you get a 3. 3 gets carried over to 48. That's 512. 512. And 2 to the 8, my goodness. 2 to the 8 is 256. Still not true. All right, keep going. Eventually we know. Eventually we know exponential wins. Okay, eventually. Okay. The evil cube function cannot win forever. It must be defeated. Okay, so 9 cubed is 81 times 9. 81 times 9 is 9. This is 72. So 729. 2 to the n is, this is 5, 1, 2. That's still not true. What about 10? Well, 10 cubed, that's easy. That's just 1,000. And 2 to the 10, that's 1,024. So this is now true. What about 11? What about 11? I think this is the light at the end of the tunnel. So 2 to the n finally win. I think when this is now finally true. So what happens is as follows. So let's do the final calculation. 11 cubed is 121 times 11. 121 is 11 squared. 121, 121, 1331. That's 1331. But you see here, after doubling of 1024, you get 2048. And I don't think anything after any n after 10, anything after starting from 10, I think starting from 10, 2 to the n is always greater. Is always greater than the cube function. So basically, if we graph this situation, and here's basically what happens. We're going to use a continuous curve, but really this is a discrete sequence, okay? So n cubed is a function that grows like this. Say it's like this. This is n cubed. Okay, so here, this is 2 to the n. 2 to the n behaves like this. This is 2 to the n. there is a small part where 2 to the n is lower than n cubed, but eventually 2 to the n prevails. So I think 10 should be our sufficiently large n. This should be big N. This should be the big N. So we're going to postulate, not postulate, but make a conjecture, not postulate. Okay. Conjecture is something that you attempt to prove. Postulate is something that you never try to prove. Simply assume that's true and then do the deduction after. Conjecture is something that you suspect is true. It's not assumed to be true. So that's totally different. Okay, conjecture is that when little n is greater than or equal to 10, we have n cubed less than or equal to 2 to the little n. So that's our second example. So we wanted to prove this. Can we do that though? And the thing is, usually when it comes to inequality proofs, there's not a whole lot of assumption you can use, right? So it's like here, of course, in the induction, we can create induction hypothesis. So that's some hypothesis to work with. But usually, let's say, if you wanted to prove this inequality without induction, how will PMI hold here? The base case inductive statement. Very good question. Here we're going to do the exploration here. This is our conjecture. So the base case would be n equals 10. Right. Let's just tentatively put base case n equals 10, so, because everything might get modified in the proof, final proof. But this is our base case here. When n equals 10, then n cubed is 1,000. 2 to the n. 2 to the n is 1024. So therefore, n cubed is less than or equal to 2 to the n. This is true, holds. So that's the base case. And now let's do the inductive step. Inductive step. So you assume m cubed is less than or equal to 2 to the m for some m. So that's the induction hypothesis. For some m greater or equal to 10. It has to include the base case. For some m greater or equal to 10. So that's induction hypothesis. And what we need, right? We need m plus 1 cubed to be less than or equal to 2 to the m plus 1. This is what we need by assuming the induction hypothesis. So how do we get there? So it might be a good idea to examine the two sides, right? So first, let's consider the right-hand side. The right-hand side is 2 to the m plus 1, which can be written as 2 to the m times 2, which by the induction hypothesis, this is greater or equal to m cubed times 2. Yeah, we shift the base case to 10 instead of 1. How do we get into no and infer such base case is required in a general setting? Do we need to do manual computation? Yes. Yes. Here, you can start with an arbitrary base case. That's the modified PMI statement. The modified PMI statement so how is this modified? So the original PMI statement treats n equals 1 as the base case. The modified version use some integer n naught. We don't know what that is a priori, but if p of n is true, and for every integer m greater or equal to n naught, p of m implies p of n plus 1, then we can say p of n is true for all n greater or equal to n naught. But in this example, the statement says n cubed is less than or equal to 2 to the n for sufficiently large n, which means this statement is really saying there exists a big N. There exists a big N in the set of natural numbers such that for all little n greater or equal to big n cubed is less than or equal to 2 to the n. The exact point where that happens is unclear. Okay. Sometimes you don't need the exact threshold. So this is the watershed moment. N equals 10 is a watershed moment here. After, since n greater or equal to, so starting from n equals 10, everything includes n equals 10 and after satisfies the inequality. And this is what we mean by sufficiently large n. The cutoff point is usually unclear, and you usually need to do manual computation or, well, using numerical experiment. Right. So this is where the exploration part is useful. Okay. It's not clear where the big N start. And just like in analysis proof, right? In analysis proof, often the scratch work consists of finding the big N. You need to construct the big N and verify the inequality after. And verify this inequality here, this part. So what we're doing here is this. The existence of big N is found through exploration. Found by exploration, which takes ingenuity. And this part, we hope, our hope is to use induction. And here we're doing that. We're trying to construct an induction proof. And by doing, and to do so, we start by exploring the two sides of our goal. We need this. So let's consider the right-hand side. We want to use induction hypothesis, so let's write it this way. So we know the right-hand side can be written as 2 to the m times 2. And that's what? That's greater or equal to m cubed times 2. Okay, that's all we can say about that. And the left-hand side, what do we do with the left-hand side? Well, the obvious choice is to expand, right? You know something about m cubed. It makes sense for us to do that. So left-hand side, after expansion, use the binomial theorem, you get m cubed plus 3m squared plus 3m plus 1. Okay, so we want to organize. So now you have a new goal. Okay, so now we want something like this. So given that we want 2 times m cubed to be greater or equal to m cubed plus 3m squared plus 3m plus 1. Right? And for that, you need m cubed to be greater or equal to 3m squared plus 3m plus 1. Is that true, though? Well, we haven't used something. We haven't used m greater or equal to 10. We haven't used that yet, so hopefully that can help. A great complication is that the powers aren't the same. Right? You see, you have cube, quadratic, and linear. Perhaps we can do something about that. Okay, so when we know that for all, we know note for all m greater or equal to 1, we have m squared greater or equal to m greater or equal to 1. We have that. So maybe we can say we can write it this way. So this right-hand side, this new right-hand side, 3m squared plus 2m plus 1 is greater or equal to, hang on. Okay, actually, you know what? Here, let's construct an upper bound for this one. So, so this way we have 3m squared plus 3m plus 1 plus 1. This is less than or equal to 3m squared. Let's leave that unchanged because I want to homogenize the exponent plus 3m squared and then plus m squared. Right. Right, this is true, and this combines to 7m squared. Is 7m squared less than m cubed though? Because this is an upper bound for the right hand side. We want to show the right hand side is less than or equal to m cubed. The upper bound of the right hand side, 7m squared, is m squared greater or equal to 7m squared. Is this true? Well, this is equivalent. Is this true? This is equivalent, remember, this is equivalent to m greater or equal to 7, but we already have m greater or equal to 10. So this is true. Yay. We're done. So we're happy. So that's the exploration for the inductive step. And now you start from m greater or equal to 7 and write everything backward. How would we know and infer such a base case shift is required in general setting? We don't. We don't. Actually, the reality of research is quite usually just a question, a conjecture. It takes a lot of manual verification for individual cases. It's a gritty reality, right? Think about the Riemann hypothesis. Okay, so now we've done our exploration. Finally, we can write the proof. Okay. So we claim, we prove. Okay, we prove. Okay. This statement. We prove n cubed greater less than or equal to 2 to the n for all integers n greater or equal to 10 by an induction on n. Okay. Okay. So this is this green part here. This is our kitchen, which is smoky and messy. It's hot and sweaty. Here, the proof is the dining hall. Okay. Okay, let me close this off. Okay, that's fine. So here, I'm just saying that the exploration can be messy, can be filled with mistakes, ideas that doesn't work, with drawings and whatnot. But in the final proof, everything needs to be polished. This is a customer experience. Okay, this is the apprentice experience in the kitchen, and this is a dining experience. So everything needs to be polished. And so the customer don't need to know how the dish is made. You know what I'm trying to say? The customer does not need to know how this scratch work, how the exploration is done, but the customer must be able to verify and that every step is true. Okay, so customer has the right to audit on the quality of the output, but he or she doesn't need to know the details of the exploration. Okay, so there we go. We prove this by induction on n. Let's start with the base case. N equals 10. N cubed in this case is 1000. 2 to the n is 10 to the 24th. Sorry, no, it's 10. Is what am I talking about? 2 to the n is 1024, and therefore n cubed is less than or equal to 2 to the n. That's the base case. Okay, and now let's do the inductive step. So for the inductive step, we start by assuming the induction hypothesis. So assume for some m greater or equal to 10, for some integer m greater or equal to 10. The idea is whenever, it's also a nice habit to have, whenever you introduce a symbol, you declare its nature. There exists, in real analysis, we often write, oh, there exists a epsilon. It's assumed that epsilon is a real, right? Even though we don't always write that, we should. Okay, but that's typically a convention in real analysis. We can kind of get away with that. It's just a nice thing about writing mathematics. Whenever you use an abstract symbol, we declare its nature. For some integer m greater or equal to 10, the inequality is true. We have the inequality is true, which is m cubed less than or equal to 2 to the m. Okay, this is our induction hypothesis. Okay, and now let's put forward our goal. Need to show m plus 1 cubed is less than or equal to 2 to the m plus 1. Okay, so how did we get there? How did we get there, right? So we start from the base case. Sorry, we start from the final step in our, not the step, okay, in our final conclusion in the scratch work. Okay, so to do so, note that here, since m is greater or equal to 10, which is greater than 1, we have the following. We have m cubed greater or equal to m greater or equal to 1. And also m greater or equal to 7. These are all immediate from the assumption m greater or equal to 10. Then we have the following. M cubed is greater or equal to 7 m cubed. And 7m cubed is greater or equal to 3m cubed plus 3m. And first, actually, let's write equality. 7m cubed is now decomposed into 3m cubed plus 3m cubed, and then plus m cubed. Okay, the first 3m cubed is left unchanged, and the second 3m cubed is greater or equal to 3m, and the last m cubed is greater or equal to 1. So we have that. All right, and then we add m cubed. This way you get 2m cubed is greater or equal to m cubed plus 3m squared plus 3m plus 1, which is exactly m plus 1. Oh, hi Vernon. Sorry, I didn't answer to your message. So this is m plus 1 cubed. And now we use induction hypothesis. By the induction hypothesis, 2 to the m plus 1 equals 2 times 2 to the m, which is greater or equal to 2 times m cubed. Okay, and now we use our previous conclusion. This is greater or equal to m plus 1 cubed as needed. This is the step where we use induction hypothesis. You can write an IH on top of the precise inequality where we use induction hypothesis. Okay, so that's it, as needed. As needed, and we can say, finally, as by the principle of mathematical induction, therefore by PMI. Okay, n cubed less than or equal to 2 to the n for all n equals 10, 11, 12, and so on. Okay, so that's it. Okay, so that's the proof. You see the proofs might be a little bit shorter than the exploration / scratch work, right? So this is the finished dish. Okay, this is what customer gets to enjoy, aka the reader. The reader should be able to verify each step along the way, but reader has no obligation to know exactly where to each step is motivated, how each step is motivated. That belongs to the scratch work. Okay, so this is the kitchen, this is the dining hall. So therefore, if you don't know the fundamentals of proofwriting, if you don't know how to say construct the proof, namely how to do the scratch work and then rewrite the proof backward, reading this proof can be perplexing. Like, how on earth am I supposed to know this manipulation of inequality, right? That's the most common question for beginners. Well, that's because the author did the scratch work. So whenever you see something like this, and you don't know how exactly each step is motivated, you can verify it is true, but you don't know where it comes from. Try to do the scratch work yourself. Okay, right. So these are two examples of induction, and I'm going to give a controversial example. This is the next example, which is also very important. I mean, you guys might have seen this because it came from my complex variable stream, but now I'm not going to use complex numbers, but just real numbers. The point is the same. So this example is the famous triangle inequality, or generalized triangle inequality. Generalized triangle inequality. Which says the following. Which says for all integers, for all n in big N, positive integers, and x1 all the way to xn, and all, right, these are all real numbers. X1 all the way to xn are real numbers. Okay, you have the following inequality. In R, okay, we have x1 plus x2 plus all the way to xn absolute value less than or equal to x1 absolute value plus x2 absolute value okay, plus all the way to xn absolute value. So that's the generalized triangle inequality. Okay, so I want you guys to pay attention to what should the base case be. And so this is the crux of the lesson. What should the base case be? What should the base case be? Okay, so when doing this proof, whenever you do a proof, you always assume something. You always assume something. You can assume that the triangle inequality for n equals 2 is proved. Okay, so we can assume so here this is our remark. Assuming the classic triangle inequality is proved. Namely, a plus b absolute value less than or equal to a absolute value plus b absolute value. So how do we prove the generalized triangle inequality? Right. So we start by saying we prove the inequality by an induction on n. Okay, so start with the base case. N equals 2, right? Hi, Wriggle. Thanks very much for joining the stream. So what if we do n equals 1? The Wriggle says n equals 2 should be the base case. If we do n equals 1, what happens? So let's just write n equals 1, then the inequality, then the statement would be x1 absolute value less than or equal to x1 absolute value. Of course, this is trivially true. This is true, trivially. Okay, and let's do the inductive step. So let's do the inductive step. Assume the triangle inequality holds for some n equals for n equals m for some m. Assume for some m in big N, you have the triangle inequality, which is x1 plus all the way to xm absolute value is less than or equal to x1 absolute value plus all the way to xm absolute value. That's what we assume. This is the induction hypothesis. All right, and what we need to show this is true for actually, let me put that down. I need to declare and say for all real numbers x1 and xm. Okay, for some m in a set of natural numbers, and for all x1 all the way to xm in a set of real, the following inequality holds true, and we need to show the following. So we need to show here x1 plus all the way to xm plus xm plus 1. Okay, this is less than or equal to x1 absolute value plus all the way to xm absolute value plus xm plus 1 absolute value. And we need to show this is true for all real numbers, x1 all the way to xm and xm plus 1 in real. So that's what we want to show. This is our goal. Okay. Note that you can break this. Okay. Usually, I mean, it's the same idea of proving summation formula. You group the first m terms together. So this would be x1 plus all the way to xm, and then plus xm plus 1. Okay, and now I'm going to use the classic triangle inequality. The absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. So this is less than or equal to xm plus xm. Okay, I want you guys to later question and critique this proof to see if there's anything wrong with it. Okay, so this is the classic, which I call classic triangle inequality, with two terms. Okay, so and now you can use induction hypothesis and write x1 absolute value plus all the way to xm absolute value, and then plus xm plus 1 absolute value. So this step we use induction hypothesis. So let's put an IH on top, and this is our goal. So we can write as needed. Okay, and finish off with a final sentence and say by PMI, the generalized triangle inequality holds for all n in big N, for all x1 all the way to xn in R. We have x1 plus all the way to xn absolute value less than or equal to x1 absolute value plus all the way to xn absolute value. And we're done. Okay, so do you guys think this is okay? Do you guys think this is okay? So we had a controversy over this when I was doing my complex variable marathon live stream. A complaint I received from chat is that you don't have so let's just call, okay, so let's consider this statement. Let's call it, denote this as P1. Okay, this is P of n, the statement P of n. What do you mean by I don't? You don't what? You don't object to this, or you don't agree with this? I don't think it's okay. Okay, perfect. So now we have a little bit of a controversy here. Right? So if the statement is denoted as Pn, the chat complaint on the complex variable live stream about the inductive step is that we don't have P1 implies P2 because P of 1 is this is trivial. P of 1 is a tautology. Does P of 1 implies P of 2? Does P of 1 implies P of 2? So there's a little bit of a controversy here. So P of 1 is a tautology, and P of 2 is a classic triangle inequality, of course, right? This is P of 2. So P of 2 can be proved on its own, right? So P of 2, here we're assuming the classic triangle inequality, and we can prove it. And we, of course, I mean, if we're only assuming it, we can prove it separately. But P of 1 is a tautology. So Chad was having a debate with me whether P of 1 implies P of 2. Their argument is that in P of 2 doesn't, to prove P of 2, you don't, P of 1 on its own does not imply P of 2 because P of 1 doesn't really say anything. That's the idea. So therefore, the knock-on effect don't happen. Right? So you don't have P of 1 implies P of 2. But I think the way I put it, like I explained it this way. Okay, I try to defend my position this way. So this was the proof I pretty much I wrote, okay, for the complex variable stream. So I don't think even one would call the form of P of 1 to be a triangle inequality. So this is, I mean, of course, P of 1 is true, and based on our formulation, right, of the statement, and there's nothing wrong with that, right? If n equals 1, this is still true. This says nothing, right? It's less x of 1 absolute value less than or equal to absolute x1. It's totally trivial. It's true, but it's kind of meaningless. It's kind of pointless, right? That's the idea. So Chad was having a debate with me whether P of 1 implies P of 2. So I was saying P of 1 is true and P of 2 is true, so true implies true is true. So therefore, you do have P of 1 implies P of 2. From a logical standpoint, you have P of 1 implies P of 2. And here, when we use the triangle inequality, we're actually using P of 2. So we are able to get P of 2 implies P of 3. And then afterwards, P of 3 implies P of 4, so the chain is unbroken. The chain of falling dominoes isn't broken anywhere. So I thought it was okay. Right. So let's consider the alternative. Okay, let's consider the alternative. If we say base case is n equals 2, if we say base n equals 2, then you can either prove the base case from scratch, or you say, okay, this is already proven. This is a classic triangle inequality. But either way, okay, n equals 2 is the classic triangle inequality. It has to be proved separately. And then in the inductive step, here you would explicitly say, okay, this is due to the base case. This step is due to the base case, or n equals 2. Right. So as we can see, it doesn't matter whether you choose n equals 1 as the base case or n equals 2 as the base case. The classic triangle inequality either has to be assumed or proved independently. So as long as that's done, my position is that it makes no difference, because it's just a matter of presentation, really. If you write n equals 1 as the base case, as I did here, you would still need P of 1 implies P of 2 to satisfy the second hypothesis in the principle of mathematical induction. You need for all positive integers m, P of m implies P of m plus 1. Okay, so here you have P of 1 implies P of 2, even though they seem rather unrelated, because proving P of 2 independently is a requirement. And you can argue that P of 1 is useless in proving P of 2 because P of 1 is a tautology, right? X absolute value less than or equal to X absolute value. That's not saying anything. P of 2 is proved independently of P of 1. But regardless, from a logical standpoint, P of 1 is true, P of 2 is true. So therefore, P of 2 needs to be, or the classic triangle inequality is either assumed or proved independently, regardless which you choose n equals 1 or n equals 2 as the base case, so it doesn't matter. This is a quirky example. Actually, this is more common than you think. This kind of statement is very common. So you have a statement that involves two terms. Okay, let's say if you have a statement involving two terms, and you want to generalize it for any finite number of terms. This actually happens a lot. Right? So for example, in measure theory, we have a notion called algebra. The algebra has an axiom which says if A, okay, is a member, A is a set, okay, is a member of a collection of a subset called F, and B is also in that collection, then you can have A intersect B, then you must have A intersect B is in the same collection. So A and B are subsets of a total set. So this is big omega, that's the universal set, and this is A, and this is B. Okay, it just says that the intersection of two elements which are sets in a collection of subsets of omega have their intersection also in the same collection. So this is the axiom. If this is an axiom, you can prove that for any finite collection, you would have the intersection of AN is in F. AI, okay? I goes from 1 to n. So there's a lot of statement that goes like this. So it's like you have a property that's true for operation that involves two terms, and then you can immediately generalize that to a statement about an operation that involves finitely many such terms. And also an example from complex analysis. So we know there's a property about the norm of a sort of norm or modulus of a complex number. So this is z. Z is a complex number x plus iy. Its modulus is defined as the square root of x squared plus y squared. And there's a property that says z1 times z2, complex multiplication, okay, has a modulus equals z1 modulus times z2 modulus. You have that property. And then you can prove, okay, for finitely many complex numbers, z1 times all the way to zn, modulus is z1 modulus times all the way to zn modulus. Now, such examples there's a lot. So you see, this is in the same, you have the same situation with this generalized triangle inequality thing. Right. The controversy really lies in whether P1 implies P2. We know individually that P of 1 is trivially true, and P of 2 is also true individually. So the connective, right? So the connective imply does produce a true statement from a logical standpoint. But this feels weird, right? This feels weird to a lot of people. It's like saying the sun rises from the east, which is a true statement. It implies today is August the 18th, which is also a true statement. So from a logical standpoint, you can put any true statement, however unrelated they may be, into a new connective and call that a true statement. It doesn't violate any logical law, but it feels nonsensical from a quote-unquote real-life logic perspective, right? So I think at this point I would concede and write the base case as n equals 2. I would concede and write n equals 2 as the base case. Because this way, because in either situation, no logical rule is violated, but when n equals 2 is treated as a base case, it feels, it's more consistent with real-life logic, even though both forms are mathematically speaking okay. It's just that for readability purpose, I think n equals 2 should be taken as a base case, even though technically speaking, as long as P of 2 is proved independently, mathematically speaking, it's okay. So that's my final verdict on this. So from a readability standpoint, I would change base case from n equals 1 to n equals 2, but I don't think n equals 1 as a base case is wrong. Okay, so let me change that now. So n equals 2 as a base case. And this is P of 2. This is because, you know, the thing is, mathematical logic or formal logic is a model. It's not meant to encapsulate all forms of deduction. Okay, so that's my take on this. For example, this imply symbol, it only models certain aspect of logical deduction, right? So it's, as I said, if you put two true statements together, connected by the imply symbol, however unrelated they may be, there's still a true statement in a logical sense. It does not violate any formal logical rules, but it's not a valid deduction in general. Okay, it's not a valid deduction in general. So it might be nonsensical. It's not wrong, but it is well, it's perhaps beyond description of mathematics. You know, classic logic was not prepared for this. Okay, they're simply unprepared for this. So to make the flow a bit more natural, let's use n equals 2 as a base case. Okay, so assume n equals 2. And this will actually removes any doubt whether P of 1 implies P of 2. That's another advantage. Because, as we shall see in the next fallacious example, you don't have P of 1 implies P of 2, P of 1 is trivially true, and you don't have P of 1 implies P of 2, and the whole proof falls apart. So for that purpose, we're going to start with n equals 2 as the base case. So x1 plus x2 absolute value less than or equal to x1 absolute value plus x2 absolute value. This is the classic triangle inequality, which it's a good exercise to prove this as a standalone exercise. Proving the classic triangle inequality is a good standalone exercise. It also takes a little bit of a scratch work to get to the actual proof. Okay, so here there's no issue over whether P of 1 implies P of 2 anymore. Okay, you start from n equals 2, and we say n equals 1. When n equals 1, the statement is true trivially. Note, n equals 1 is trivial for n equals 1, it is trivially true. Okay, so here, yeah, you can just say this is a base case. I think this flows a lot better. Okay, so speaking of which, that's the promised false example. So false proof on all the horses have the same color. Okay, so that's the thing I was warning about. So it really boils down to whether you do have P of 1 implies P of 2 or not. If you don't have that, then the whole induction proof falls apart. And you can have ridiculous statement like this. Here, this is a screenshot because writing this is a bit tiresome. Okay, so the following is a well-known example of a quote-unquote proof, which means a false proof, that all horses have the same color. Right. So yeah, the implied symbol is just a shorthand for a specific truth table. It does not encapsulate like all requirements to form a logical statement. You see, the idea is, if let's say, if a deduction violates the formal rules we have for all these connectives, then certainly you don't have a valid proof, right? That's I think that's called a formal fallacy in logic, not in mathematical logic, but the logic in philosophy. So in philosophy, you have this formal fallacy versus informal fallacy. Okay, this formal fallacy versus informal fallacy. A deduction that, you see, is an error in the structural logic. That's a formal fallacy, or a form of an argument, making it invalid regardless of the content. You see, the whole project of mathematical logic is to abstract away the content of a proposition. Right? You denote a proposition as P, Q, right, and assign truth value to it. The content is abstracted away. The informal fallacy is an error in the context or meaning of an argument, meaning the structure may look valid, but the reasoning is still fail. Right, so here's the example. Do you have an example? Formal fallacy, affirming consequent. If it rains, the street gets wet. The street is wet, therefore it is raining. Right, it fails because a sprinkler or a burst pipe could wet the street. This is because implication is not equivalent to its converse. That's a logical fallacy. That's a formal fallacy, right? Because we know the truth table of P implies Q and Q implies P aren't equivalent. Right? From the truth table, those two statements aren't equivalent. And we actually, you know what? We cooked up the definition of imply partly because of it. The definition of imply, right, especially the definition of the vacuous truth, is not God-given. We define it this way so that we don't have implication equivalent to its to its converse. We explained that multiple times. Right? Why vacuous truth is needed is so that this sort of argument don't get validated. So this is a formal fallacy, and informal fallacy is context-based, right? Content is context-dependent and content-based. Right, so this is an example. John is a rude person. John says carbon tax is bad. So therefore, John's argument against the carbon tax is wrong. Right? This actually happens a lot in real life. Right? We all seen such example. Right? This is appealing to the person's character. Right? Right? So there. You know, it's like saying, because the sun rises from the east, and therefore today is August the 18th. It does not violate any formal logical rules, but that's a fallacy, right? Because based on the context, you cannot make that deduction. Okay, I'm not a philosopher, okay, so that's all I'm going to say about that. So even though here in our earlier writing, that P of 1 is true and P of 2 is true, putting them together does not violate any logical rules. It just doesn't. It's okay logically, but you still have to manually check whether P of 1 implies P of 2, right? So that's the whole thing. Here, if you write the base case as n equals 2, there's no need to check P of 1 implies P of 2 or not. It'd be simply because, well, it starts from n equals 2 anyway. The knock-on effects start from n equals 2 anyway, and n equals 1 is a trivial statement. So here, you also have a similar situation, and let's see where the proof is wrong. Oh, okay. Sorry. Yeah, so the invite link, I'll change that like right now, actually, guys. Sorry about that. I'll change that right now. The Discord invite link gets expired every now and then, and my bad. Okay. Sorry. I'm gonna change it like right now. I'll put it in chat as well. Okay. My apologies. I need to update it like every week. I don't know when exactly it gets expired, but yeah, this is the new link. It should work now. Let me know if you have any issue, and I'll change it in the channel description. So yeah, this is so basically what we did earlier. This is not an isolated kind of weird example. There's a lot of statement that is true for kind of a binary situation. You have two terms and the statement is true. An operation, it involves two terms and the statement is true. The operation is associative, and you want to generalize it for arbitrary number or finitely many numbers of terms. In that situation, I think it's better to start from n equals 2, just for the sake of readability and the flow of the argument, to remove the controversy whether P of 1 implies P of 2. Okay, so okay. Anyway, here we have that's the Discord link. Let me change that. Okay, so the change is now completed. So it should work now. Okay, so that's the fallacy. Okay, so the two forms of fallacy: formal versus informal. Here we have a proof that all horses have the same color, and let's analyze exactly where it could go wrong, where it went wrong. Okay, so Pn denote the statement: for every set of n horses, all the horses in the set have the same color, are the same color. We prove for all n in z plus, this means just begin, okay, the natural numbers, P of n by induction on n. note that P of 1 is true, since for any set containing a single horse, all the horses in that set have the same color, namely the color of that single horse. This is stupid, but it's true. Okay, this is of course trivially true. Next, let m greater or equal to 1 and assume that P of m is true, i.e. for any set of m horses, all the horses in the set are the same color. Okay, that's the induction hypothesis. We prove that P of m plus 1 is true. And this is the argument. Okay, let S be the set of m plus 1 horses named x1, x2. Let's write that down. Okay, so this is a new set for m equals 1. For m equals 1. Okay, so you got the set x1, x2 all the way. Okay, let's write x3 as well, because that's needed. x3 all the way to, this is m greater or equal to 1, supposedly. Okay, m greater or equal to 1. That's positive integer. Okay, m greater or equal to 1. And all the way to x of m plus 1. xm plus 1. So this is the new set. You have m plus 1 horses. Okay, we're going to use the induction hypothesis on the subset x1 all the way to xm. Well, because x1 all the way to xm, right, are a set of m horses. So they have the same color by the induction hypothesis. And now what? Furthermore, the horses x1, x3 all the way to xm plus 1. So now you have a second subset, which is x1, x3, skipping x2, all right? Blah, 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 all the way to xm and xm plus 1. These all have the same color as well. And because these two sets have intersection, which is x1, among other things, right? They have intersection, including x1. They intersect. These two subsets, they intersect. Therefore, they have the same color. It follows that all of them have the same color, since they're all the same color as the horse x1. x1 is a common element. Therefore, P of n plus 1 is true. It follows by PMI that P of n is true for all n, i.e. all horses have the same color. What is wrong with this proof? Okay, so guys, can you think of a reason why this is, what is wrong with that? Like, feel free to contribute in chat, because this is a classic fallacy when it comes to induction. You see here, this is a sneaky thing. This is a sneaky step where we skip x2, right? We skipped x2 and kept the rest. What's wrong with that? Well, what's wrong with that is because when m equals 1, you cannot skip x2 and go to x3. I'm going to spoil the answer, okay? I'm doing it now. When m equals 1, you can skip to x3. You can't skip x2 and go to x3. It doesn't work. So essentially it boils down to P of 1 does not imply P of 2. It doesn't work. So what happens at P of 2? So at P of 2 you have a subset. You have a set S equals just two horses, right? x1, x2. Okay, so to use the induction hypothesis, namely P1, you want to go from P1 to P2, right? Induction hypothesis would be P1, P of 1. So in that case, you only have two subsets, right? Two subsets that are singletons. P of 1 only applies to singleton, right? So you have two subsets, singleton subset. Which is x1 and x2. And they have no common element. Right? Remember here, in the final argument where we conclude all the horses have the same color, because they have the same color as x1. Here, when m is greater or equal, actually, when m is if you can skip x2, and m is greater than 1, if you can skip x2, then x1 would be a common element. Right? The two subsets, x1, x2 all the way to xm, and the other subset, x1, x3, and so on all the way to xm, xm plus 1, have a common element x1. Here, the two singleton subsets has no common element. Have no common element. So you cannot reach the final conclusion. You cannot reach, okay, these two sets all have the same color. So therefore, P of 1 does not imply a P of 2, and the whole knock-on effect don't happen, and the proof falls apart. Okay, so here in the if I revert back to the old writing, say n equals 1 as a base case, right? You would have to individually check whether P of 1 implies P of 2. Right? From a logical standpoint, as I said, that's true, but P of 2, right? P of 2 has to be proved independently, because P of 1 isn't very useful, right? So there you go. That's the this is where it can fail. So be careful about that. Okay. So for this kind of statement, similar to the generalized triangle inequality situation, I recommend using n equals 2 as the base case, and simply remark n equals 1 is a trivial and move on. Right. So that's the our introduction on standard induction. Okay, but I also wanted to talk about strong induction. I mean, once again, despite the name, it's not actually stronger. I really dislike the terminologies about proof by induction. It causes so many potential confusion. First of all, the proof by induction is a method in deductive reasoning. It has nothing to do with inference. Okay. Finding some specific example and generalize it has nothing to do with that. It's all about checking assumptions and reaching a conclusion, and that's the fundamental structure of the induction proof. You check two hypotheses and reach a conclusion. And the foundation is really the definition of positive integers. The foundation is really the Peano axioms. Okay, so here we're using induction as a proof technique, right? That's the whole point of the video, of the live stream. But induction is also how integers are defined in the first place. So really, the foundation of induction, right, the principle of mathematical induction is equivalent to a bunch of things. Principle of mathematical induction is equivalent to also so-called the well-ordering principle. The well-ordering principle. The well-ordering principle is something we used in one of our sessions in Zurich, which I got confused. So you can check out my post on the weekend. I think it was last weekend. Oh, actually, I didn't put out a quiz today. I just... Oh, there was no quiz today. Okay, we'll make that up later. So this is a post, and I was trying to prove this statement. For every q is a real number, okay, q greater than 1 fixed, then for every positive number x in R, there exists a unique integer k such that q to the k minus 1 less than or equal to x less than q to the k. So that's a statement. So this is a statement about real numbers. So q is a real number, that's fixed. And we want to prove this is true for arbitrary x. You can bracket, basically you can bracket any real number by two consecutive terms in a geometric progression. So that's the lemma. Okay, and the proof needs the so-called well-ordering principle. The well-ordering principle says every non-empty subset of Z that is bounded below has a least element, and the least element is unique. Okay, usually it's just the existence part. I mean, in textbook, the well-ordering principle only states the existence part, but the uniqueness part is trivially true. So this statement is equivalent, in fact equivalent to PMI. You can prove that the well-ordering principle to be equivalent to PMI. So fundamentally speaking, PMI is a statement about the nature. You can treat it even as an axiom. It's an axiom about integers, positive integers. It has nothing to do with quote-unquote induction in a philosophical sense. So yeah, unfortunately the terminology survives and it creates confusion. Okay, so here this is nothing. This is not the fault of students or readers. It's simply the outdated, in my opinion at least, the outdated terminology that is doing the damage here. It's kind of like imaginary number, still confusing today whether those numbers exist or not. These aren't mathematical fiction. They exist. They are just as real as real numbers. It's just that the unfortunate terminology, the historical baggage, survives. And here we have another historical baggage, namely strong induction. So this one is in particular a nonsensical terminology. Let me explain why. First, we will write down the statement of the principle of strong induction. Strong induction. So this is how it works. Theorem. Principle of strong mathematical induction. Okay. So the or PSMI. Okay. So once again, let P of n be a statement about the positive integer n. So that's the and now we have the hypothesis. Okay, this is PSMI1. First you have P of 1 is true. PSMI2 says, okay, if for all m in big N, if P if for all integers k equals 1 all the way to m, P of k is true. If then P of m plus 1 is true, Okay, this is PSMI1, PSMI2. Sorry, this is PSMI2. If you have these two, then it follows that you can reach the conclusion, which is the same as in the standard principle of mathematical induction. You can conclude that for all n in big N, P of n is true. Just say P of n. So that's the conclusion. So here, what is the principal difference, right, between principle of strong mathematical induction and principle of mathematical induction? Remember, in PMI2 here earlier, in PMI2, you only need to assume P of m. Right? P of m implies P of m plus 1. But here in the strong induction, you need to prove, so you need to assume P of m and every statement before, which is P of 1, P of 2, all the way to P of m. So this is a distinguishing feature of strong induction. Okay. Strong induction assumes for all integers k equals 1 all the way to m, pk is true. Compared to regular induction, only assumes Pm. So the induction hypothesis says more. So that's the difference between principle of strong induction and regular induction. You know, I'm always perplexed by the terminology here, because usually we can compare the strengths of statement in two ways. Okay, a statement is an implication. If P, then Q. Okay, if you assume P, then Q, right? then Q must be true. That's pretty much all the statement in mathematics. You have an assumption and a conclusion, right? If two statements have the same assumption, okay, and let's say if this is the usual structure of the statement, P implies Q. Okay, this is statement 1, S1. Say this is P implies Q1. And statement 2 says P implies Q2. That is to say, they have the same hypothesis, but the conclusion is the same. But the same hypothesis, the conclusions are Q1 and Q2. They might not be the same. Let's say if Q1 implies Q2, then we say S1 is stronger. Then we say S1 is stronger. Does that make sense? Because Q2 is already contained in Q1. Is the truth value of Q2 is already decided by Q1. So S1 is a stronger statement. Right. So for example, let's give an example. Let's say Donald Trump is the current US president. Okay. So P is the person's name is Donald Trump, and Q1 is Donald Trump is that person is the current US president. Okay. And let's say keep the same P1, let's keep the same P, that's Donald Trump, the person's name is Donald Trump, and Q2 is that person is a US citizen. But of course, we know if a person is a US president, he or she must be the US citizen, right? So the first one is stronger. It makes sense. This is one way to decide whether a result is stronger or weaker. But then again, you can have another way to decide whether a statement is stronger. So now let's say you have Q being the same conclusion. You have P1 implies P2. The intuitive idea is that in this scenario, if you have the same conclusion, right, the proposition that assumes less is stronger. That makes sense? If two implications have the same conclusion, but one has fewer assumptions, the one with a fewer assumptions is like the Occam razor principle, right? The one with fewer assumptions is the stronger statement. Okay, so that's the Occam razor in action. But here, in PSMI, we are actually assuming more. But this is a strong induction. It's kind of weird, isn't it? This is such an odd terminology. Okay, but leaving that aside, we can. This is a pre-statement. Okay, this is just a name. The PSMI is just a name. I really don't get the terminology. Okay, I mean, this is my objection to the terminology. I think this should all be changed. But you know, the thing is, induction and strong induction, they're used so pervasively. I mean, throughout literature, changing this would be a daunting task. But at least we know what this means. Okay. So here is basically strong induction. In one of his hypotheses, assumes the desired statement is true for all integers k equals 1 to all the way to m for some m. And you want to make use of not necessarily all, but at least one statement that is before say p of m, right, or prior to p of m, to deduce p of m plus 1. That's the strong induction. And I also explained my objection to the terminology strong. Hopefully that makes sense. Okay, I have no idea why this concern has never been raised in textbooks and maybe professors. I don't know. Like, I never heard any objection to this terminology, but I personally think this is really confusing terminology. And the thing is, you can actually prove that PSMI and PMI are mathematically equivalent. So really, the strong induction is no stronger or weaker than PMI. It's just a different form of induction, really. Yeah, despite the appearance that you are assuming more in PSMI2, okay, the overall statement, hypothesis, conclusion together, it is equivalent to the ordinary induction. It's just a more convenient way to use the principle of induction. Sometimes you need, okay, say p of m minus 1 as well. So we prove this equivalent form of the induction statement so that you don't always need to justify that step. So this is really what it is about. This is the same principle. Fundamentally, this boils down to, once again, the axiom of positive integers. Okay, PSMI is no stronger, quote unquote, stronger. If let's say if it's really stronger than the usual PMI, if it's really stronger, okay, in the usual sense we use the word, that means PSMI would imply PMI, but not the other way around. But no, okay, it is a mathematical fact that theorem. Okay, we're not going to prove this one, but I'm just going to state it here so you there's no confusion about it. I mean, you can prove it as an exercise, but the theorem, it says that PMI and PSMI are equivalent. You can start from PMI and prove PSMI, and you can prove the PSMI. You can assume PSMI and and then prove PMI. Okay, you can do that. And this is an exercise in the Larkin's book, the main book we follow for the introduction to proof series. So actually, I'm going to leave it here. Okay, so this is we're going to read the overall strategy. You can prove this. Okay, this is a sketch of proof, but that's not our main focus here. Okay, we're not going to spend the actual effort trying to prove it, but you can do this. So here, this is the guided exercise. We'll just read through it, okay, to see the basic idea. In this exercise, we will prove that PMI is logically equivalent to PSMI. In other words, given PMI, show that you can deduce a statement PSMI and vice versa. Okay, so that's I think this further solidifies our criticism towards the terminology here, because this creates unnecessary mental friction that PSMI is somehow quote-unquote stronger than PMI. It's not. They're logically equivalent. And also, really just a convenient way to apply the principle of induction, aka the fundamental axioms of integers. Okay, so you can assume that PSMI is true. To prove that PMI is true, let P of n be a statement about positive integer n. Okay, and assume that P1 is true. You see, assume what? Assume you want to use, right? You want to use the assume statement, which is PSMI. So you gotta assume that the two hypotheses of PSMI is true. So you assume that P of 1 is true, and for all, oh actually, yeah, so, sorry, never mind. To prove your goal is to prove PMI is true. So to prove PMI is true, PMI is implication, right? It's PMI is implication, which means if PMI 1, PMI 2, you want to prove the conclusion of PMI, namely for all n greater or equal to say 1, P of n is true. So to prove PMI, okay, so prove PMI, you have to assume PMI 1 and PMI 2 and deduce this as a consequence. And for that, in the deduction, you need PSMI. Okay. Your goal is to prove that. So this is 1 and 2 here. These are PMI 1. Assume this is PMI 1. Okay, regular induction. PMI 2. PMI 2. Your goal is to prove for all n in Z plus P of n is true. You should do this using PSMI. To do this using PSMI, meaning we have to verify the assumptions of PSMI. Right? So in order to use this PSMI here, where's that? To use PSMI here, you have to verify PSMI 1 and PSMI 2. Assume PMI 1, PMI 2, you wish to prove this is PSMI 1 and PSMI 2. Okay, I know this is confusing. Basically, PMI is our goal. PMI is an implication. PMI is an implication that says PMI 1 plus PMI 2 implies for all n, P of n is true. Okay, so to do so, we assume the if part of PMI, PMI 1 and PMI 2, and our goal is to prove for all n in Z, P of n is true. And to do so, we need to use PSMI because that's what we assume in this direction. Okay, and you see, because of the conclusion of PSMI 1 is also for all n in Z plus P of n is true, we just need to verify the assumptions of PSMI. Okay? So that means verifying PSMI 1 and PSMI 2, or verify. So that's the overall strategy. And now, if we do the reverse direction, that is to say, we assume PMI 1 is true. Assume PMI 1 is true. We want to prove PSMI is true. Well, to prove PSMI is true, PSMI is also an implication. It says PSMI1, PSMI2 implies for all n in big N, P of n is true. So therefore, you start by assuming the if part of PSMI. That is to say, you assume PSMI1, PSMI2, and now we need to verify. And now we need to verify PMI1 and PMI2. So that's the logical flow of this proof of equivalence. Okay, this is not critical for applications of the strong induction or induction, but this is just to clarify the logical foundation here. The two methods aren't really, say, strong or weak than another from a logical standpoint. In fact, they're logically equivalent. It's just that PSMI is a convenient shortcut for applying induction. Okay, so I hope I didn't just confuse everyone by stating this. Okay, first of all, the terminology is, in my opinion, screwed up. It's not really stronger or weaker than regular induction. The distinguishing feature of PSMI or strong induction is that in PSMI2, you kind of assume more, right? You assume no. What am I doing? My goodness, I'm an idiot. This is for some. Oh, actually, yeah, this is for all. This is for all, sorry. This is for all. This is for all. Yeah, this is for all m. Yeah, this should be for all m. So you assume more. You assume P of 1 true, P of 2 true, all the way to P of m true. And you want to prove P of m plus 1 is true. And in the process of proving P of m plus 1 true, you're going to use some, okay, perhaps not all, but some statements among P of 1 all the way to P of n, if that makes sense. Okay, so you have these two overall strategies for proving statement like for all n, in big N, P of n is true. So the question arises, which one should you use, right? Should you use the regular induction or the strong induction? What I do normally, okay, well, this is an experience thing, right? What I do normally, unless, say, I'm absolutely sure that a regular induction would do it, like, for example, proving a summation formula, I know regular induction is most likely, like this one, most likely to nail it, right? So unless it's super obvious based on experience that a regular induction would seal the deal, I would actually start by assuming PSMI2. Okay, I would assume for all integers, okay, for all integers k in 1 all the way to m, P of k is true for some m. If I end up using, okay, more than one statement among P of 1, P of 2 all the way to P of m, if I end up using more than one statement in the assumption, in the hypothesis, then well, that means you really do need the strong induction. If not, if I only use the final one, if I only use P of m, then I will change it to the regular induction. So that's the way I tend to go about proving stuff using induction. Of course, this has to do with scratch work as well, right? When you do the scratch work, it will become clear whether you need just P of m or statement prior to P of m. What I usually do by default is actually starting from the induction hypothesis for the strong version, if that makes sense. Okay, because I hate to say only assume P of m Okay, and I can't do the proof because I need something prior to it. Okay, so therefore I start with the strong version. That's just my personal preference. Okay, once again, it's experiencing. It's how we construct proof. Is how I construct proof. Okay, so there's that. Let me give two examples for the strong induction. Okay, so as we said earlier, summation formula like this one, the sum of arithmetic progression, is an obvious candidate for regular induction. Is there any obvious candidate for strong induction? There is. Okay, once again, this is just a purely empirical thing. Okay, there's no mathematical theorem that says, okay, whenever you see this summation formula, use the regular induction. No, it's just a experience thing. Okay, but here I'm going to give you another classic form of problems that involves strong induction, namely higher order recurrence relation. This is example. Which example? No, this is example what? 3? I don't even know at this point. This is example 2. Okay, this is example 3. This is example 4. All right. The example 4 says we're dealing with a higher order recurrence relation or difference equation. Same thing. Higher order recurrence relation. So that's the typical candidate for using strong induction. So it says here, it says for all n greater or equal to 2, an plus 1 equals an plus 2 times an minus 1. Okay, and you have a of 1 equals 1, a of 2 equals 5. The goal is to find an explicit formula for a of n and then prove it. Okay, so if you know the general theory about linear difference equation, then this question is very simple. Okay, and you can even argue there's no need for induction. But here we're going to use an explore and then verify approach. Okay, we're not assuming prior knowledge about theory of linear difference equation. And by the way, as a side tangent, we solved something similar to this one in our stream on integral transform, in particular the z transform, which is essentially the generating function of the series. Here, over there, we use the Fibonacci sequence as an example. This is also a higher order difference equation. Basically, higher order difference equation means in the recurrence relation, it involves 2 or more than 2 terms prior to the term with the largest index, if that makes sense. Okay, so here f of n in the classic difference equation, the classic difference equation for the Fibonacci sequence, f of n is f of n minus 1 plus fm minus 2. So that's an example of a second order Fibonacci sequence. All right, and here we are also dealing with an plus 1 equals an plus 2 times an minus 1. So that's an the gap, so to say, the gap between the largest and the lowest index is 2. Okay, so find an explicit formula and then prove it. So you can
for example, use the technique of generating function to do so, but I'm not going to do it. Okay, so because this is very much an introductory video, live stream, series, whatever you want to call it, and we don't assume any advanced knowledge over these specific techniques. Okay, so first let's start with exploration, as usual. So this is A1 is 1, A2 is 5. What's A3? A3 is, by the recurrence relation, to get a feel of the problem. So that's A2 plus 2 times A1, which is 5 plus 2, that's a 7. Right, that's a 7. That's A3. A3 is a 7. Okay, what's A4 then? A4 is, looks like what? It is A3 plus 2 times A2. That's 7 plus 10, which is 17. Let's do A5 to see what's the pattern here. Okay, A5 is A4 plus 2 times A3, which is 17 plus 2 times A3 is a 7. A3 is a 7, so that's hang on. Did I make a mistake here? A1 is 1, A2 is 5, A1, A3 is 7, A4 is 7 plus 10, 17. Okay, so right. So this is correct. So the 17 plus 2 times 7, that's a 14. 17 plus 14, that's a 31. And so on. Can we notice there's a pattern going on here? They're kind of close to the powers of 2. Right? So they're kind of close to the power of 2. Let's compare them. Okay, so here, this is A, N. This is N. Okay, let's do the table here. So observe that you have N equals, this is 1, 2, 3, 4, 5. There seems to be a pattern here. Oh, there must be. So A1 is 1, A2 is 5, A3 is 7, A4 is 17, A5 is 31. So this is kind of close to 2 to the n, isn't it? It's kind of close to 2 to the n. So here, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5th is 32. And what's the difference? The difference, top minus bottom. Okay, so that's a minus 1. And that's a 1. That's a minus 1. It alternates. It's a 1, it's a minus 1, and so on. So here we make a conjecture that an is 2 to the n plus minus 1 to the n. Can make that conjecture for all n greater or equal to 1. Okay. So of course, verifying the base case is easy. In fact, there should be 2 base cases. There should be 2 base cases. P of 1 and P of 2 is true. You can base cases. We call this, say, P of n. Okay, the base cases include P of 1 and P of 2. Right? That's the 2 initial values. They're given, right? So, indeed, they are true, right? According to our table here. So this is a base case, and to do the inductive step, so this is your an. You now want to go to, say, an plus 1, right? An plus 1. But the thing is, an plus 1 requires, by the recurrence formula, it not only needs an, it also needs 2 times an minus 1. So it would be nice if you can use the same formula, the same explicit formula, but with now n equals n minus 1. So this means not only you need to assume Pn, you also need to assume Pn minus 1. So the expression for an is Pn given by Pn, given by the statement Pn. And the expression for we would like to use P of n minus 1 in the inductive step. So for that, let's use strong induction. We assume, okay, there exists an integer n such that, okay, P of 1 is true, P of 2 is true, all the way to P of n is true. So this suggests a principle of strong mathematical induction. So that's the intuition here. Okay, and now let's write the proof. So as I was saying, because here it's obvious that you would need not just an, but also term prior to it. For higher order recurrence relation, PSMI is an obvious choice. I'm not saying obvious is a high probable candidate, okay, for using PSMI. All right, so there's that. Okay, so let's do the actual proof. We'll do this proof, and we'll do a classic proof as a final reward, so to say, of today's session, which is the fundamental theorem of arithmetic, the proof for integer factorization, integer prime factorization. Okay, so let's do this proof. Let's wrap this up real quick. So because you already have the conjecture, you just need to verify it. Okay, so we prove what by induction? We prove an equals 2 to the n plus minus 1 to the n for all n greater or equal to 1 by induction. But actually, we will emphasize this is a strong induction. Yeah, because whenever you use strong induction, you should say so up front. Okay, if it's just a plain induction, it means, well, plain induction. By a strong induction on n. So the intention is now declared. The base cases are P of 1 and P of 2. So A1 is 2, A1 is 1, okay, A1 is 1, and the formula says 2 to the 1 plus minus 1 to the 1 is also 1. Therefore, okay, so let me do that later. Let's also verify for A2. Okay, so for A2, you have 5, okay? 2 squared plus minus 1 squared, that's a 5 as well. Therefore, an equals 2 to the n plus minus 1 to the n, for n equals 1, 2. Okay, actually, let's clarify. Base cases include n equals 1 and 2. All right, so now you have the base cases. Let's do the inductive step. Okay, so let's first start by writing the induction hypothesis as always, but this time for strong induction. So we should write, assume for some m, okay, assume for, the thing is, we wanted to use, you see, we want to use the recurrence relation, therefore the m must be greater or equal to 2. Okay, be careful about that. For m greater or equal to 2, otherwise you might call for a term that don't exist. So there you go. So that's for some m equals 2, we have am equals, you want the formula Actually, no, not just AM. Okay, a strong induction needs to include here for some m greater or equal to 2, and for all integers, here m should also be an integer. Okay, for all integers k equals 2 all the way to m. For all integers, we have a k equals 2 to the 2 to the k, yeah, plus minus 1 to the k. This is our inductive hypothesis. As required by the principle of strong mathematical induction. Okay, so that's it. And then what we need to show a m plus 1 is 2 to the m plus 1 plus minus 1 to the m plus 1. So that's our goal here. And of course, to do so, we use the recurrence relation. So by the recurrence relation slash difference equation, okay, since m is greater or equal to 2, we can use the recurrence relation am plus 1 equals am plus 2am minus 1. Actually, here, you see, I made a mistake. I made a mistake here. I made a mistake because in the inductive step, you see, for PSMI2, k needs to go from 1. It's not just 2. You can't just use 2. You need to go from 1. Because, for example, say, if we wanted to check A3 satisfy the same formula, you would need A1 and A2. So you need A1. You can't just start from 2. You need A1 as well. So for some k greater or equal to 2, first of all, for some integer m greater or equal to 2, that is the upper bound for k needs to be the base case with the largest index, n equals 2. And then once that upper bound is fixed, for every k starting from 1 or whatever lowest integer in the original statement needs to be, it can be n naught, k needs to start from the same minimum number. Okay? So here n start from 1, so k needs to start from 1. Because if you don't have k equals 1, then A3 is unavailable. Okay? So that's a mistake. Okay, I corrected it. Okay, learn from that mistake. Okay, so here you have this recurrence relation, and then we can finally substitute all the formulas. Okay, say m greater or equal to 2, am subscript greater or equal to 2, m minus 1 is greater or equal to 1. And that's no problem. We can use the formula. You can use the formula given in the inductive hypothesis. You can use inductive hypothesis by IH here. am is now what? Is 2 to the m plus minus 1 to the m plus 2 times, all right, 2 to the m minus 1, and then plus minus 1 to the m minus 1. Okay, otherwise, if you don't have k equals 1, this substitution might be invalid. And now just algebra. Okay, right now at this point it's just straightforward algebra. You get 2 to the m plus, okay, here you have 2 times 2 to the m minus 1, so that's another 2 to the m. And here you can write it as plus minus 1 to the m that's this term right here, and write minus 2 times minus 1 to the m. Okay, so the first two terms gets combined into 2 times 2 to the m, which is 2 to the m plus 1. Okay, let's write 2 to the m times 2. And here you got a minus 1 to the m. Okay, when this is the same as 2 to the m plus 1 plus a minus 1 to the m plus 1, and we are done as needed. Okay, and to finish this up, let's write by the principle of strong induction by PSMI. Okay, you have the formula an equals 2 to the n plus minus 1 to the n for all n in the set of natural numbers, and we're done. Okay, so the bottom line is, for higher order recurrence relation like this one, proving its property, including in particular for explicit formula. Okay, why did I write two formula? Find an explicit formula and then prove it. Okay, so that's the sort of question that typically involves strong induction. It's kind of like the summation formula. Okay, it's like the number one candidate for using strong induction. All right, so that's the process of strong induction. Okay, we know how to write induction hypothesis. Actually, let me highlight the key syntax. Okay. You can apply the syntax even when you don't know what you're doing. It's kind of making baby step towards constructing the final goal. Here, we emphasize we use a strong induction. Okay, so base case. Here, the base cases are obvious because these are the initial values. Sometimes, once again, base case requires a little bit of exploration. An inductive step. Okay, this is in particular quite critical for all integers k. This is too much. Let me choose a milder color like this one. This is a distinguishing feature of strong induction. Using a strong induction meaning assuming this. So these are all mandatory syntax. And also where exactly we need to show, this is also needed. Where exactly we use induction hypothesis by PSMI. Okay, so that's kind of parallels with the situation in our first example, the summation formula proof. See, these are mandatory sentences or components, whatever you want to call it, in a strong induction proof versus the mandatory components in induction proof. Okay, chat has been real quiet. Like, I don't know, like, do you guys agree with my criticism towards the terminology of strong induction? Because I feel like this has caused some confusion. Okay. Anyway. Okay. So we'll prove the final result, and then we'll wrap things up. Okay. So hopefully this is a self-contained introduction to induction proofs. And this is a celebrated result. Celebrated result is the fundamental theorem of arithmetic, the existence of prime factorization. I believe this was first done by Euclid. Although I don't know whether Euclid used induction to prove it or something else. But I have personally never seen a proof that isn't based on induction. But once again, my experience with number theory is very much limited. So do take what I said about number theory with a grain of salt. Okay, the fundamental theorem of arithmetic, the existence part. Of course, prime factorization is unique up to, well, a reordering of factors. So the existence part is easier, so it's proven here. The uniqueness part requires more results in number theory. After a while, mathematicians just call both induction after we know they're equivalent. Yeah. But once again, these are for mathematician. Like, this is insider knowledge. So if you're trying to learn the material, it might cause confusion, right? So that's how I think about it. So here, the fundamental theorem of arithmetic existence part says the following. It says for every positive integer n, n greater than 1, can be written as a product of primes. That's basically it. I.e., that says for every positive integer n, for every n in the set of big N and n greater than 1, there exists a positive integer s such that and there exists a prime. There exists prime prime p1 all the way to ps. Doesn't have to be distinct. Okay, primes p1, finitely many primes basically, ps, such that n equals p1 times all the way to ps. Prime factorization, right? We all know this from elementary school. Every positive integer greater than 1 can be written as a product of prime. And to do so, we need the definition of prime. So what's the definition of prime? Right, we all know this since high school, or even elementary school, but let's just actually define it properly. Definition of prime. The definition of prime says, okay, if a number, say, is, how can we formulate the definition of prime using, logical quantifiers and whatnot? Okay, recall. Okay, n in the set of natural numbers is a prime right, if n is greater or equal to 2. So 1 is not a prime. N is greater or equal to 2, and whenever n equals a times b for some integers a and b, for some ab in the set of natural numbers, A or B must be 1. A equals 1 or B equals 1. So that's the definition of prime. Right? So it has no positive factors, integer factor, other than 1 in itself. This is the definition of prime. So let's try to prove it using induction. Okay, so let's think about how do we prove it. Right? First of all, start with the base case. And the base case is trivial. So the base case is obviously n equals 2. So this is our scratch work. Let's begin with scratch work. N equals 2, this is obviously true. Right? Okay. Well, how do we do the inductive step? This is the base case. So we face a choice whether we should use strong induction or just regular induction. Let's consider regular induction. Right? So regular induction would be assume for some m greater or equal to 2, there exists m greater or equal to 2 integer, okay, so that m has a prime factorization and you want to show you need m plus 1 also has a prime factorization. But there's a problem, isn't it? But there's a problem because it's not always possible to go from P of m go to P of m, okay, P of m alone to P of m plus 1. But this is a problem here. Issue. The regular induction has issues. Say, for example, let's consider m equals 8. What are the prime factors of a? Well, it's just 2 times 2 times 2. And m plus 1 is 9. The thing is, the prime factorization of m plus 1, that is 9 in this case, has nothing to do with the prime factorization with, well, its predecessor, or 3. So you cannot make use of P of m directly. So regular induction doesn't work, or it's awkward to write, right? So it doesn't work. So instead consider strong induction. So what do we do? Well, we would assume there exists m greater or equal to 2 so that what? So that the statement is true for all integers greater than 1 but smaller or less than or equal to m. So it's just that 2, 3 all the way to m, right, has prime factorization. And then we need to show you still need the same thing. You still need m plus 1 has a prime factorization. And now what? Now you can easily finish off the proof. Okay. First, let's consider the trivial case where the successor m plus 1 is already a prime. If it is already a prime, then it is its own prime factorization. So we can just consider the case where m plus 1 is composite, which isn't a prime. Okay, so let's put that here. If n greater or equal to 2 is not a prime, It's called composite. Okay. So if this is already a prime, then there's nothing needs to be done. If it is composite, what? If it's composite, then you can write m plus 1 equals a times b, where none of a and b are 0. A and b are not 0, but not 1, but strictly greater than 1. That's it, right? These are integers that are strictly greater than 1. The thing is, you already assume, and by the induction hypothesis, a and b have prime factorization. A and b, by the induction hypothesis, a and b have prime factorization. PF. So you're done. So that's the idea of the proof. It feels like cheating, isn't it? Right. Okay, so this is where the principle of strong induction really shines. It's awkward to go from P of M to P of M plus 1. There's no indication that the original statement, namely the existence of prime factorization, would require strong induction, unlike the previous problem, right? So in the previous problem, you're dealing with a high order recurrence relation. This obviously calls for a strong induction, as argued earlier. But this one is not clear. You really need to explore the statement a little bit more to see that, oh, regular induction does not work very well. So let's use strong induction. So let's start with the actual proof. We prove the statement by strong induction on n. Right, that's it. Right, that's the overall strategy. And let's start with the base case. N equals 2. So 2 equals is its own prime factorization. Yeah. So that's done. Okay. So that's it. All right. So inductive step goes like this. Okay. So we're going to follow the PSMI. Assume what? Assume for some integer m, m greater or equal to 2, for some integer m greater or equal to 2, for all k equals 2, right here you should start from 2, not because of m greater or equal to 2, but because of in the statement the lowest such integer is 2. So 2 all the way to m. For each of these k has a prime factorization PF. Okay. Right. What do you need? You need to show m plus 1 has a prime factorization. Okay. Let's consider two cases. Case 1. M plus 1 is already a prime, then there's nothing to be proved. Right, so that's trivial. And in the second case, where m plus 1 is composite, or is not a prime, then m plus 1, okay, equals a times b, for some integers a and b that are greater than 1. So that's it. Okay, so in that case, we have then in that case both a and b, a would be greater or equal to 2 and less than or equal to m. It cannot equal to m plus 1 because otherwise b would be 1. And same with b. A and b are both greater or equal to 2 and less than or equal to m. And that's exactly the range where the inductive hypothesis here, this is the inductive hypothesis I forgot to add. Okay. Here you can use inductive hypothesis on A and B. Okay, and therefore by inductive hypothesis, A and B both have prime factorization. And of course, the product of those two, therefore, the product of those two, m plus 1, and hence m plus 1 equals a times b, has a prime factorization, right? Just the prime factorization of a times the prime factorization of p, and we're done. So therefore, finally, by the principle of strong induction, by PSMI, every integer that is greater than 1, every integer n file is getting longer, so it's getting laggier. Okay, so for every integer n greater than 1, fortunately just the last sentence, has a prime factorization. That's just the existence part. We haven't showed the uniqueness part. But you see it's actually pretty short. Without strong induction, this would be pretty awkward to prove. All right, so that's it for today. Just to summarize what we did. Okay, so we introduced both proof by induction and proof by strong induction. I mean, two proof common techniques which are really based on the same foundation, namely the definition of integers, the definition of positive integers. Okay, here you need to verify the base case and inductive step, and we have outlined the common, the mandatory syntax for writing proof by induction style proofs. Okay, a common candidate for proving for proof using regular induction is the summation formula. Okay, and the principle of mathematical induction can be modified so that the base case is an arbitrary, not an arbitrary, but for some integer. It does not necessarily has to be 1. And to find the base case sometimes requires a little bit of an exploration. Okay, and next up we emphasize there's potential danger on whether P of 1 implies P of 2. And in the case where if you don't have P of 1 implies P of 2, obviously you don't have a proof. And in the case where P of 1 is trivial and P of 2 is proved independently of P of 1, well, if P of 1 is trivial and P of 2 so proving P of 2 would be not, sorry, let me just put it this way. If P of 1 is trivial, it would not be useful for proving P of 2. In those situations, we would prefer writing the base case from n equals 2. Okay, so this way you don't need to individually check whether P of 1 implies P of 2. Okay, so this is actually pretty common. For, say, you have an operation that works for the binary operation, let's say you have a binary operation that is associative, then typically you can generalize properties for that binary operation that involves only 2 terms to finitely many terms. For those kind of proofs, we start by n equals 2 as the base case. Okay, so that's here we have a pitfall where you don't have P of 1 implies P of 2 and the whole proof falls apart. And next up, this is strong induction. Despite being mathematically equivalent to regular induction, right, in the technique by strong induction, you need to assume not just one statement, say P of M, but all the preceding statements as well. Okay, and obvious candidate, high probable candidate for using strong induction is higher order recurrence relation, and a classic theorem, which is the existence of prime factorization. That pretty much wraps it up for today, and I'll see you next time. Thank you.